Have you ever wanted to go back in time, to see moments unfold in reverse? Imagine if time itself started moving backward, planets retracing their paths, stars returning to their birth, and every event rewinding. What would that look like? Could the universe really work like that? These are the questions scientists are beginning to explore as they delve into the mysteries of time reversal. Could time ever truly run backward? And what would that mean for everything we know? How we think about time. From the moment we wake up, it's there, time. Tick-tocking away as we glance at our clocks, count the minutes until lunch, or wait for the weekend. It's so constant and predictable that we rarely stop to question it. We accept that time is linear, like a one-way street that only goes forward. But what if it didn't have to? What if time could move backward too? Not just in our daydreams or regrets, but in reality. It's a strange thought, right? The idea that time, the force that seems so unchangeable, could be more flexible than we think. That maybe, just maybe, it's not as straightforward as it feels. Let's take a step back for a moment. Time, as we know it, feels like this ever-present flow. We move through it without really understanding it. Think about it. As we grow older, we see its effects on our bodies. Our hair grays, our skin wrinkles, and the world around us changes. Children grow up. Buildings crumble and are replaced. The seasons change. It's all a part of what we know as time, and we rely on it a lot. We use it to make sense of everything around us. Time gives structure to our lives. Appointments, schedules, anniversaries. Even the smallest tasks are tied to time. You know what time to wake up, what time to go to work, and what time you'll get to eat your favorite meal. But that's because we all share this common understanding of how time works. It goes forward. And that makes sense to us. That's the world we know, but is it really the only way, the only direction? Let's picture for a second what it would mean if time moved backward. Imagine looking at a sunset, only to watch it rise again instead. Or picture a spilled glass of water. Watch as the droplets on the floor slowly leap back into the glass, as if nothing ever happened. It's strange, yes, but think about how it would change everything we understand. There's something comforting about time moving forward, isn't there? We know that our past is behind us, and the future is ahead, waiting to unfold. We count on it, we trust it. But the idea of time moving in the opposite direction, unwinding events, feels unsettling. And yet, it's a possibility that some scientists have considered. Our lives are filled with constant reminders of time's forward march. You see it when you look in the mirror and notice another grey hair or wrinkle. You see it in your loved ones, in children as they grow taller, and in the face of an aging grandparent. Time's movement feels inevitable. Everything that lives eventually changes, grows, and fades away. Think about the clock on your wall. Every tick brings the future closer, and as those hands spin, they remind us that time is something we can't stop. No matter what we do, it's always moving forward. But clocks are just tools we use to measure time. They don't define it. Time itself is more mysterious and complex than a ticking second hand. If time wasn't locked into moving forward, our entire understanding of the universe would shift. Every event, every memory would be open to change. Imagine being able to undo mistakes or relive your greatest moments. But also think about how disorienting it would be to experience the future before it even happens. In a world where time could flow backward, would anything really be permanent? Einstein's theory of relativity and the nature of time. One of the most groundbreaking ideas in modern physics, thanks to Albert Einstein, is that time isn't as fixed as we think. It's actually relative. That means time can change depending on a few key factors, like how fast you're moving, or how close you are to a massive object, like a planet or a black hole. Let's break that down. Einstein's theory of relativity turned our understanding of time on its head. In everyday life, we don't really notice time behaving strangely. A minute on your watch is the same minute on someone else's watch across the world. But when we look at extreme situations, like objects moving near the speed of light, or places with incredibly strong gravity, we see that time doesn't behave the way we expect it to. First, let's talk about time and speed. Imagine you're sitting on a spaceship traveling close to the speed of light. You look at your watch and everything seems normal. Minutes and hours tick by just like they always do. But if someone was standing still and watching you zoom by from Earth, they would see something very different. From their perspective, time would be moving slower for you. The closer you get to the speed of light, the slower your time passes compared to someone who's not moving at all. This phenomenon is called time dilation. It sounds wild, but it's been tested and proven by scientists. In fact, we've even seen it in action with astronauts. The International Space Station, for example, moves incredibly fast around the Earth, about 17,500 miles per hour. Because of that speed, time actually moves a tiny bit slower for astronauts aboard the station compared to people on Earth. We're talking about fractions of a second, but the effect is real. If you were able to travel even closer to the speed of light, the difference in time would be far more dramatic. Let's say you had a friend who took off in a spaceship traveling at 99% of the speed of light. They go on a journey to a distant star, and the trip takes them 5 years. When they return, they'll have aged 5 years. But you, back on Earth, might have aged decades. Time for them passed more slowly, while for you, it kept moving forward at its normal pace. That's time dilation at work. Einstein's theory also tells us that time behaves differently depending on how close you are to a massive object, like a planet, a star, or, most dramatically, a black hole. This is known as gravitational time dilation. Here's how it works. The stronger the gravitational field, the slower time passes. To understand this, picture two people with identical watches. One person is standing on a mountain, far away from Earth's center of gravity, while the other is standing at sea level, closer to the planet's gravitational pull. If you let both people go about their day and then check their watches at the end, you'd find something strange. The person at sea level, where gravity is stronger, would have experienced time more slowly than the person on the mountain. Again, the difference is incredibly small, but it's there. Now, let's take it to the extreme, near a black hole. Black holes are so massive, and their gravitational pull is so strong that they warp time in ways that are almost unimaginable. If you were to float near the edge of a black hole, time for you would slow down drastically compared to someone watching from a safe distance. From their point of view, you'd appear frozen in time, as if you weren't moving at all. But for you, time would still feel like it's moving normally. This effect is so strong that, theoretically, if you spent a short time near a black hole and then returned to Earth, everyone you know might have aged decades or even centuries, while you only aged a few minutes or hours. Einstein's relativity shows us that time is flexible. It can stretch, slow down, and speed up depending on your speed or the gravitational forces around you. This concept changes everything we thought we knew about time being a constant, unchanging force. So, if time can stretch and shrink, that leads to a big question. Could it move backward? If we know that time can behave differently based on speed and gravity, could there be conditions where it doesn't just slow down or speed up, but actually reverses? The idea of time moving backward seems like something straight out of science fiction, but Einstein's theory opens the door to all sorts of questions about the nature of time and space. One of the things that makes this idea so intriguing is that Einstein's equations for relativity work just as well if time moves forward or backward. Mathematically, there's nothing stopping time from reversing. But in the universe we experience, time only seems to go in one direction, forward. That's because of something called entropy, which is the natural tendency of systems to move from order to disorder. It's why broken glass doesn't reassemble itself, and why we grow older, not younger. Entropy gives us the sense that time has an arrow pointing forward. But there are theories that suggest if we could manipulate gravity or speed in the right way, we might be able to reverse the arrow of time. For example, if you were to travel faster than the speed of light, something Einstein's theory says is impossible for now, time could theoretically reverse. You'd move backward through time, like rewinding a movie. One theory from the world of quantum mechanics, where time seems to behave even more strangely. In the quantum world, some particles appear to act as if they're moving backward in time. This doesn't happen on a scale we can see, but it raises the question of whether time reversal could happen in extreme, unusual conditions. Stephen Hawking's views on time reversal. Stephen Hawking was one of the most influential physicists of our time, and he spent much of his career pondering the mysteries of the universe, including the nature of time. Among his many contributions to theoretical physics, Hawking delved into some of the more mind-bending aspects of time travel, including the possibility of time reversal and the concept of closed time-like curves, paths in space-time that might allow for loops, effectively letting someone or something travel back to earlier points in time. Hawking approached time travel with a deep understanding of the complexities involved, but he also maintained a level of skepticism. He was well aware that, while time travel, especially backward time travel, makes for fascinating thought experiments, it brings along significant challenges and paradoxes, like the grandfather paradox. Nevertheless, he explored the theoretical frameworks that could allow time travel under certain extreme conditions, such as near black holes or in the presence of exotic matter. One of Hawking's most well-known contributions to the discussion on time travel was his idea of the chronology protection conjecture. In essence, this theory suggested that the laws of physics would ultimately prevent time travel on macroscopic scales to avoid paradoxes and logical inconsistencies. Hawking proposed that even though some equations in general relativity allow for time loops or time travel, there would likely be a protection mechanism in place, ensuring that such phenomena wouldn't occur in reality. The idea was that the universe somehow protects itself from the chaos of time travel paradoxes by preventing them from happening in the first place. At the same time, Hawking didn't completely dismiss the possibility of time loops, especially when it came to closed time-like curves. These curves represent solutions to Einstein's equations of general relativity, which describe how space-time behaves under the influence of gravity. A closed time-like curve, if it exists, would be a path through space-time that loops back on itself, allowing an object, or even a person, to travel along that path and end up in the past. In other words, you could follow the curve and return to an earlier point in time, creating a loop. Closed time-like curves arise from certain theoretical solutions to general relativity, and they are most famously associated with extreme space-time configurations, such as those found near rotating black holes, or in the case of wormholes, hypothetical shortcuts through space-time. Hawking, however, was cautious about these ideas. While closed time-like curves are mathematically possible, he believed that the universe would likely prevent such time loops from forming, or if they did form, they wouldn't be usable for practical time travel. One of the more well-known models for closed time-like curves involves rotating black holes, also known as Kerr black holes. In this model, if you could travel close enough to the event horizon of a rotating black hole, it's possible that space-time could be twisted in such a way that you could enter a closed time-like curve. As you followed this path, you might find yourself looping back in time. The idea here is that the intense gravitational pull and rotational energy of the black hole warp space-time to such an extent that time and space begin to behave in unusual ways, potentially allowing for time loops. Hawking's views on time reversal and time loops were shaped by his deep understanding of quantum mechanics and general relativity. He recognized that the math behind closed time-like curves worked, at least in theory, but he also believed that something about the universe, perhaps quantum effects, would prevent these loops from becoming a reality on a macroscopic scale. One of the problems with closed time-like curves, according to Hawking and other physicists, is that they open the door to paradoxes. If time loops are possible, then it would be theoretically possible to go back and alter the past, leading to contradictions like the grandfather paradox. Hawking believed that the universe must have a built-in mechanism that prevents these kinds of paradoxes from happening, which is where his chronology protection conjecture comes into play. In the context of quantum mechanics, Hawking also speculated that quantum effects might create a kind of feedback loop that would prevent the formation of closed time-like curves. When particles interact at a quantum level, they follow probabilistic rules rather than deterministic ones. Hawking suggested that any attempt to create a closed time-like curve would result in quantum fluctuations or disturbances that would destroy the loop before it could form. Essentially, the very attempt to manipulate time would cause the universe to self-correct and block the time loop from ever happening. While Hawking was generally skeptical of the possibility of large-scale time loops, he did acknowledge that closed time-like curves could exist in some extreme scenarios. For instance, certain solutions in general relativity allow for closed time-like curves in theoretical objects called cosmic strings, long, thin objects that stretch across the universe and have immense gravitational pull. If two cosmic strings were to pass by each other at high speeds, it might be possible to create a closed time-like curve between them, allowing for time travel. However, the energy required to manipulate cosmic strings or other such objects would be astronomical, making it unlikely that closed time-like curves could ever be used for practical time travel. Despite his skepticism, Hawking remained open to the idea that the universe might allow for some forms of time manipulation, particularly in the context of quantum mechanics. He believed that while the universe would prevent large-scale time loops, there might still be situations at the quantum level where time behaves in ways that we don't yet fully understand. Quantum mechanics, with its inherent unpredictability, allows for strange behaviors that seem to defy our usual understanding of time, such as particles interacting across time, or even reversing their motion in certain circumstances. Hawking's work on black holes also touched on the idea of time reversal, particularly in the context of Hawking radiation. This is a theoretical process where black holes emit radiation due to quantum effects near the event horizon. Over time, this radiation causes black holes to lose mass and eventually evaporate. The process of Hawking radiation hints at time reversal symmetry, where the emission of radiation can be viewed as a black hole reversing some of the processes that led to its formation. What does it mean for time to move backwards? Time flowing in reverse would change everything. Events wouldn't progress the way we're used to. You wouldn't just wake up, live your day, and go to bed. Instead, life would unfold in reverse, a bizarre, almost dreamlike experience where cause and effect switch places. You would witness effects before their causes. Conversations would start with a goodbye and end with a hello. The way we experience life would fundamentally change, reshaping every moment we've ever known. Let's break this down even further. Think about something as simple as eating. You pick up a fork, stab your food, take a bite, chew, and swallow. In a world where time flows backward, that whole process would play out in reverse. You'd start with a full stomach, feeling satisfied, and then you'd watch as the food makes its way back out of your body onto the plate, and eventually back to where it was before you even touched it. It's unsettling to think about, but it gives you a glimpse of what it would mean for time to move backward. Imagine a conversation with a friend. Normally, you exchange words in a natural sequence. One sentence leads to another, and together you build meaning. But if time flowed backward, that sequence would break apart. You'd hear the last sentence first, then the second to last, and so on. By the time you're done, you wouldn't be building a conversation. You'd be unraveling one. It would feel like listening to a tape being rewound, with no context for the words you're hearing. Now, take it a step further, and imagine how this would impact your life. Have you ever made a mistake that you wished you could undo? In a world where time runs backward, you wouldn't just undo your mistakes, you'd unlive them. Think about a decision you regret. Instead of moving forward, reflecting on it, and learning from it, you'd watch it unravel and return to the moment before the decision was made. You wouldn't have the chance to fix things in the future because you'd be stuck living everything in reverse. It would be like erasing your footprints from the sand before you ever knew they were there. In this reality, you wouldn't just undo mistakes, you'd undo everything. Every achievement, every victory, every joyful moment would slowly unravel. Think about your proudest accomplishment, whether it's graduating from school, landing your dream job, or finishing a marathon. In a world where time runs backward, you'd experience the excitement first, and then slowly watch it fade. The diploma would return to the hands of the dean before you walked across the stage. Your dream job would disappear before your eyes, and that feeling of crossing the finish line would reverse as you retrace your steps to the starting point. Every moment you've worked for would vanish before you even realized it was happening. You wouldn't grow older, you'd grow younger. Every day would bring you closer to your birth rather than further from it. The people around you would do the same, aging backward until they eventually returned to the moment they were born. The world as we know it would be unrecognizable as everything slowly winds back to where it all began. But it's not just personal experiences that would change. The entire fabric of history would be rewritten. Imagine the events that have shaped our world. Wars, discoveries, revolutions. Everything would play out in reverse. The moon landing, instead of being a giant leap forward for mankind, would become a retreat back to Earth, with the lunar module slowly lifting off the moon's surface and returning to where it started. Historical figures who shaped our world would unlive their achievements, and the progress we've made as a society would reverse itself, one step at a time. Now you might be wondering, could this actually happen? Is time moving backwards something that's possible in the real world? Or is it just science fiction? The truth is, while it sounds like fantasy, there is real science behind the concept. Theoretical physicists have explored the idea of time reversal, and in some cases, it's not as far-fetched as it seems. One of the key ideas behind time moving backward is symmetry. In physics, symmetry is a big deal. It's the idea that the laws of nature should work the same way, no matter which direction time is moving. In theory, if the universe is perfectly symmetrical, time could move in reverse just as easily as it moves forward. But our universe isn't perfectly symmetrical. There are forces, like entropy, that seem to push time in one direction only, forward. Entropy is the tendency for things to move from order to disorder. It's why things break, why energy spreads out, and why we experience time as moving forward. In a universe with increasing entropy, time seems to be locked into moving forward, because disorder keeps increasing. But what if entropy could decrease? What if for some reason the universe started becoming more ordered instead of less? In that scenario, time could theoretically move backward. It's a mind-bending thought, but it's one that scientists have seriously considered. And while we don't see time moving backward in our everyday lives, there are hints that time reversal might be possible on very small scales, like in the quantum world. In quantum mechanics, particles behave in strange and unpredictable ways. Sometimes they even seem to act as if they're moving backward in time. This doesn't happen on a scale we can see, but it raises the question, if time reversal can happen in the quantum world, could it happen on a larger scale? Could there be places in the universe where time moves differently, where the flow of events could be reversed? Historical perspectives on time moving backwards. The idea of traveling to the past has fascinated humanity for centuries. Long before the advent of modern science and physics, people have wondered what it might be like to go back in time, to witness historical events firsthand, or even to change the course of history. This concept, while firmly in the realm of imagination for most of human history, has appeared in countless myths, stories, and philosophical musings. In ancient cultures, the notion of time was often cyclical rather than linear. Many believed that time could loop back on itself, with history repeating in cycles. Ancient civilizations like the Greeks and Hindus held cyclical views of time, where the past wasn't necessarily a place you could visit, but something that would eventually come around again. The Greek myth of the eternal return suggests that all events will eventually recur in the same form. Though not explicitly time travel, this idea reflected a deep fascination with the patterns of time and history. People believed in fate, destiny, and the possibility that history could, in a way, repeat itself endlessly. Fast forward to the medieval period, and ideas about time remain deeply intertwined with religion. Many religious texts viewed time as something governed by divine forces. In this framework, the past, present, and future were part of a grand design, orchestrated by gods or higher powers. Medieval scholars often pondered the question of predestination and free will, asking whether it was possible to alter what had already been decided by divine forces. While time travel wasn't a common theme, the idea of being able to change events, especially as part of a divine plan, laid the groundwork for future thoughts on revisiting the past. It wasn't until the Enlightenment and the scientific revolution that the concept of time began to shift towards something more linear and measurable. As scientists like Isaac Newton began to describe time as an unchangeable, constant flow, the idea of manipulating it became more intriguing. If time moved forward in a straight line, could it be possible to reverse that line, to go backward and visit the past? The philosophical debate about time and free will deepened during this period. Thinkers like Immanuel Kant questioned the nature of time itself, arguing that it was not an external force, but rather a product of human perception. Kant believed that time, as we experience it, is something created by our minds to make sense of the world. This opened up the possibility that if time was subjective, perhaps it could be altered, or even reversed, under the right circumstances. As the 19th century arrived, technological advancements gave rise to new ways of thinking about the future and the past. The Industrial Revolution and the invention of machines that could seemingly bend the rules of nature sparked imaginations about what else might be possible. It's no coincidence that one of the first major explorations of time travel in literature, H.G. Wells' The Time Machine, was published in 1895, right at the height of the technological boom. Wells's story was groundbreaking because it took the notion of time travel seriously, presenting it not as magic, but as something potentially achievable through technology. In his novel, the protagonist uses a machine to travel into the distant future, but Wells also leaves the door open for the possibility of visiting the past. This novel set the stage for time travel to become a major theme in literature and popular culture. At the same time, early scientific theories about time were beginning to evolve. The discovery of the laws of thermodynamics, particularly the concept of entropy, introduced the idea that time might have a direction, what physicists now refer to as the arrow of time. The second law of thermodynamics states that entropy, or disorder, tends to increase over time. This concept led scientists to think of time as something that moves in only one direction, toward greater chaos. But what if it could be reversed? Could there be ways to counteract entropy and move backward in time? The Big Bang and time reversal. The Big Bang is used to describe the beginning of everything we know, the birth of our universe, the moment when space, time, matter, and energy all exploded into being from what seemed like nothing. But as monumental as that moment was, there's a question that lingers in the minds of many scientists. Could there have been a moment when time itself behaved differently? Could time, which flows ever forward in our daily lives, have reversed in the early universe? It's a question that stretches the limits of our understanding of reality. The universe, as we observe it today, is constantly expanding. Everything is moving away from everything else. Galaxies are spreading apart. Space itself is stretching. And with this expansion, time moves forward, tick by tick, moment by moment, just as it always has. But when we look back, way back, into the earliest moments of the universe, things start to get strange. In the first fractions of a second after the Big Bang, the universe was an incredibly dense, incredibly hot sea of particles and energy. Time, as we experience it, had only just begun. But the closer we look at those early moments, the more it seems like time might not have been behaving in the same way it does now. To understand why this question is so compelling, it helps to think about the laws of physics. In our everyday lives, we see cause and effect. Drop a glass and it shatters. But what if the laws that govern the universe work the same, whether time moves forward or backward? In other words, if you reverse time, would the glass unshatter and leap back into your hand? On a fundamental level, some of the laws of physics are time reversible, meaning that they don't care which way time flows. This raises the intriguing possibility that, in the moments after the Big Bang, time might not have been as rigidly defined as it is now. Perhaps, in those first moments of the universe, time could have flowed in multiple directions, or maybe even backward, before settling into the forward march we know today. But how would that have worked? And what does that mean for our understanding of the universe? There are theories that suggest the universe could have gone through a phase where time ran in reverse. Some scientists speculate that in the incredibly high-energy environment of the early universe, where quantum mechanics dominates, the rules of time might have been much more flexible. Quantum mechanics, the strange world of subatomic particles, operates on a set of rules that are radically different from what we experience in our everyday lives. In this world, particles can exist in multiple places at once, move backward and forward through time, and interact in ways that seem to defy logic. So when we apply quantum mechanics to the early universe, it's possible that time itself wasn't bound to the same forward direction that we see now. One particularly intriguing idea comes from a theory known as the Big Bounce. According to this idea, the universe didn't just start with a single Big Bang and expand from there. Instead, the universe could have gone through cycles, expanding, contracting, and then expanding again in a series of cosmic bounces. During these contraction phases, time might have reversed, flowing backward as the universe shrank, only to move forward again when it expanded in the next Big Bang. The Big Bounce suggests that time might not just be a one-way street. In fact, the universe could have experienced multiple phases where time behaved in ways we can hardly imagine. In one phase, time might move forward, with galaxies forming and stars burning brightly. But in another phase, during the contraction of the universe, time could flow backward, with everything retracing its steps until the next bounce brings it forward again. The question of whether time could reverse in the early universe also ties into the broader concept of entropy. In our universe, time seems to move in one direction because of entropy, the idea that systems tend to move from order to disorder. It's why things break down over time, and why we experience time as moving forward. But if the universe were to contract, as in the Big Bounce scenario, it's possible that entropy could decrease, leading to a reversal of the arrow of time. In the quantum realm, however, time and entropy are much more flexible. On a quantum scale, particles don't necessarily follow the same rules of cause and effect that we're familiar with. Quantum particles can move backward through time, and in some cases, quantum processes are completely reversible. This raises the possibility that, in the chaotic conditions of the early universe, time might not have been tied to entropy in the same way it is now. Another perspective comes from the idea of time symmetry, the concept that time could be symmetric, meaning it might not inherently flow in one direction. If time is symmetric, the universe could have begun with a moment of perfect balance, where time could have flowed either way. Some theories suggest that our universe could be part of a larger multiverse, where other universes exist with different arrows of time. In these universes, time might flow backward, or it could loop around in ways we can't fully comprehend. Does time flow differently on other planets? Is time the same everywhere in the universe? This simple question opens a window into some of the most fascinating aspects of how time behaves in different environments. Most of us take for granted that time flows at a constant rate, whether you're here on Earth, orbiting a distant star, or standing on a moon in another galaxy. But as it turns out, time is far from uniform across the cosmos. Depending on where you are, the gravitational pull you experience, or the speed at which you're traveling, time can behave in ways that are wildly different from what we experience here on Earth. One of the strangest things about time is that it's relative. Einstein's theory of relativity taught us that time doesn't tick away at the same rate everywhere. Instead, time can speed up, slow down, or even, in theory, reverse under certain conditions. This leads us to a mind-boggling question. Could there be places or moments where time's arrow points the other way? Before we explore that, let's dive into how time might flow differently on other planets, moons, and across the universe. First, let's start with the concept of gravitational time dilation. The stronger the gravity, the slower time flows. This idea stems from Einstein's theory of general relativity, which explains that massive objects like planets and stars warp the fabric of spacetime. Think of spacetime like a stretched rubber sheet, and imagine placing a heavy ball in the center of it. The ball bends the sheet, creating a dip. The same thing happens with planets and stars, except they bend spacetime, and the more massive they are, the stronger the effect. On planets with intense gravitational fields, time actually passes more slowly than it does on Earth. This means that if you were to live on such a planet, your days would feel normal to you. But an observer from a different, less massive world would see time ticking by more slowly for you. This phenomenon doesn't just apply to planets. It extends to all celestial objects with significant mass. For instance, near a neutron star, where gravity is incredibly strong, time slows to a crawl compared to Earth. Imagine you're standing on a planet with double the mass of Earth. Your watch ticks away, seconds pass. But due to the planet's intense gravitational pull, someone on a smaller planet would experience time passing faster. You, standing in the stronger gravity, are in a sort of slow motion compared to them. The closer you are to a massive object, the slower time goes, and the further away, the faster it flows. This gravitational effect gets even more dramatic the closer you get to the most extreme objects in the universe, black holes. Black holes, with their mind-boggling density and intense gravity, warp time to an incredible degree. If you were to orbit near the event horizon, the point of no return, time would nearly stop relative to someone far away. In fact, if you spent what felt like minutes close to a black hole, whole years or even centuries might pass elsewhere in the universe. But gravity isn't the only factor that changes how time flows. Speed is just as important. According to special relativity, the faster you move, the slower time becomes. This effect is especially noticeable as you approach the speed of light. Imagine two astronauts traveling at different speeds in space. One is on a leisurely trip around a nearby moon, while the other is racing through space at nearly the speed of light. To the fast-moving astronaut, time ticks more slowly than it does for their friend moving at a slower speed. Upon returning from their journey, the fast-moving astronaut might find that while only a few hours passed for them, days, months, or even years have gone by for their companion. This effect becomes even more significant when you consider how planets and stars move through space. Some planets may orbit their stars at incredible speeds, and these differences can lead to small but measurable shifts in time. For example, imagine a planet that orbits its sun at near light speeds. Time for its inhabitants would slow down drastically, meaning they would experience much less time passing compared to life on a slower-moving planet. Now let's bring these ideas together. What happens when you combine strong gravity and high speed? You get an even more pronounced warping of time. In extreme environments, like a planet orbiting a black hole, time could pass so slowly that what feels like hours to the inhabitants might be years, or even centuries, for an observer far away. Essentially, different planets can experience time at different rates, meaning the very concept of time is fluid, depending on where you are in the universe. So, could time's arrow, the idea that time always moves forward, be reversed in certain places or moments? Let's delve into the theory behind this tantalizing idea. Physicists have long debated whether the laws of the universe could allow for time to move backward. One theory suggests that if you could manipulate the conditions around an object, such as by creating a region of negative energy, you might be able to reverse the flow of time, at least on a microscopic level. Theoretically, wormholes or hypothetical closed time-like curves, loops in space-time, could allow objects or even information to travel backward in time, creating the possibility that time's arrow could point in the opposite direction. One of the most intriguing ideas comes from the CPT symmetry in physics. CPT stands for charge, parity, and time. This symmetry suggests that if you reverse the charge of a particle, flip its spatial coordinates, and reverse the direction of time, the laws of physics would still hold. While we haven't observed large-scale time reversal in the universe, CPT symmetry implies that, under certain conditions, it might be possible. This raises the tantalizing possibility that in some distant corner of the cosmos, there could be regions where time flows backward. Of course, we've never observed time moving backward in a macroscopic sense. But in certain quantum experiments, particles do seem to behave as though they are moving backward in time. This is known as time reversal symmetry in quantum mechanics. And while it's still a hotly debated topic, it hints at the idea that time might not be as linear as we think, at least at the smaller scales. Another area of study is the multiverse theory, which suggests that our universe is just one of many parallel universes, each with its own set of physical laws. In some of these universes, time might flow differently than it does in ours. Some physicists speculate that there could be entire universes where time flows backward from the future to the past. While this remains purely theoretical, it challenges our understanding of time's arrow and suggests that in the grand scheme of things, time might not be as straightforward as it appears. Now, that's what time reversal could be like on other planets. But what about Earth? How would time reversal affect our lives? Time reversal in everyday life. Déjà vu is one of the most common examples of how time can feel like it's repeating. You've probably experienced it before. You're in the middle of a conversation, or maybe you've just walked into a room, and suddenly you're hit with the overwhelming feeling that you've done this exact thing before. Everything feels familiar, but logically, you know this moment is new. What's happening here? Why does time feel like it's looping? Scientists have studied déjà vu for years, and while they don't have a definitive answer, there are a few theories. One possibility is that déjà vu is linked to the way our brain processes memories. Our brain stores information in fragments, and sometimes those fragments can overlap in a way that makes the present feel like the past. It's as if our brain is sending us a signal that it recognizes something in this moment, even though we know we've never been in this exact situation before. Some people think is that déjà vu might be a glitch in the brain's timing system. Our brains are incredibly efficient at processing information, but sometimes things can get a bit out of sync. In these cases, the brain might mistakenly store a current event as a memory before we fully experience it. This could create the sensation that we're recalling something that hasn't happened yet, giving us the strange feeling that time is doubling back on itself. While déjà vu is not literally a time reversal, it can feel like one. For a brief moment, it's as though time has repeated itself, and we're stuck in a loop. This feeling is unsettling, but it's also fascinating because it shows how our perception of time isn't always as straightforward as we think. Now, let's talk about memory. We all know that memories can be powerful. They allow us to revisit the past, reliving moments of joy, sadness, or nostalgia. But sometimes, a memory can be so vivid, so lifelike, that it feels like we're experiencing that moment all over again, almost as if time has rewound and taken us back to that exact place in time. These vivid memories can be triggered by anything: a familiar smell, a song, or even a specific place. When this happens, we don't just recall the memory, we relive it. It's as if our brain reactivates the sensory details from that moment, bringing it to life in a way that feels immediate and real. You might hear the same sounds, feel the same emotions, or even remember the way the air smelled at that time. It's not just remembering, it's re-experiencing. In these moments, time feels like it's folding back on itself. The past and the present blur together, and for a short while, it's as though we've stepped out of the forward march of time and back into a moment long gone. But of course, we know that this is all happening in our minds. We're not truly traveling through time, but our perception makes it feel like we are. This ability to revisit the past through vivid memories is one of the ways we experience a kind of psychological time reversal. It's not as dramatic as jumping into a time machine, but it does show how flexible our minds can be when it comes to processing time. Beyond déjà vu and vivid memories, there are other ways our perception can make time feel reversed, or at least not as linear as we usually experience it. Have you ever noticed how time seems to slow down when you're bored, but flies by when you're having fun? Or how a single moment of crisis or shock can feel like it stretches on forever, with every detail burned into your memory? Our perception of time is deeply tied to our emotional and psychological state. In high-stress situations, like a car accident or a near miss, people often report that time seemed to slow down, allowing them to notice every detail. It's not that time is actually moving more slowly, but rather that our brains are processing information more rapidly, making it feel like more time is passing than it really is. In moments of extreme focus or danger, our minds shift into high gear, and suddenly, we're able to take in every second, as if time itself has stretched out. On the flip side, when we're in a state of flow, when we're deeply immersed in a task or activity that we enjoy, time can seem to disappear. Hours can go by without us noticing, and before we know it, the day is over. This experience, often called time dilation, shows that while the clock keeps ticking at the same rate, our perception of time can be anything but constant. In both cases, time isn't behaving any differently, but our brains are processing it in a way that makes it feel like it is. Whether it's slowing down, speeding up, or even feeling like it's stopped altogether, these shifts in perception give us the sensation that time is far more fluid than we usually think. In a sense, we do experience a kind of time reversal, but it's all happening within the confines of our minds. We revisit the past through memories, and sometimes those memories are so strong that they feel more real than the present. We experience the strange sensation of déjà vu, where time seems to loop back on itself, if only for a second. And in certain moments, whether of boredom, stress, or joy, time stretches, shrinks, or disappears altogether. Tachyons, particles that travel faster than light. Tachyons are not part of the everyday world, but they've intrigued physicists and sci-fi enthusiasts alike because they break the fundamental rules we're used to. If tachyons were real, they wouldn't just move quickly, they'd be faster than anything else in the universe. And that speed could have some very strange effects on how they experience time and how we could interact with them. The idea of tachyons came from the work of physicists in the 1960s, who wanted to explore what would happen if something could travel faster than light. In Einstein's theory of special relativity, objects with mass can't reach the speed of light because doing so would require infinite energy. As you approach the speed of light, the amount of energy needed to go faster increases dramatically, making it impossible for anything with mass to break that limit. But tachyons, by definition, don't play by those rules. They are particles that, if they exist, never travel slower than light. Instead of starting at rest and accelerating toward light speed like normal matter, tachyons are always moving faster than light from the moment they're created. Their existence isn't just about speed. It's about existing in a completely different framework of reality, where time and space behave in ways that are almost impossible for us to grasp. One of the most fascinating implications of tachyons is that they could theoretically travel backward in time. To understand how this could happen, let's look at how time behaves when we approach the speed of light. In Einstein's relativity, time slows down the faster you move. If you could somehow travel at the speed of light, time would essentially stop for you, at least from the perspective of someone observing you. But what happens if you move faster than light? Time doesn't just slow down, it reverses. For tachyons, the normal progression of time, moving from the past to the future, doesn't apply. Instead, these particles could experience time in reverse, allowing them to arrive at a point before they even left. This doesn't just bend our understanding of causality, it flips it upside down. Imagine throwing a ball and watching it fly backward into your hand before you even tossed it. That's the kind of paradox that tachyons could create. In fact, the equations that describe tachyons suggest that as they lose energy, they actually move faster. This is the opposite of what we'd expect from normal matter, where losing energy causes objects to slow down. In the case of tachyons, though, losing energy would mean speeding up even more, possibly reaching earlier and earlier moments in time. While tachyons are theoretical, they fit into some parts of modern physics in interesting ways. Tachyons are predicted by certain extensions of quantum field theory, particularly in the study of unstable particles and quantum states that decay rapidly. Some string theories, which attempt to unify all forces and particles in the universe under one framework, also allow for the possibility of tachyons. These theories describe tachyons as particles that could exist in high-energy environments, such as the early universe, before decaying into more stable forms of matter. One of the most curious aspects of tachyons is their relation to the imaginary mass. In physics, we calculate the mass of particles using real numbers. But for tachyons, their mass would be an imaginary number, a strange concept that leads to the possibility of faster-than-light travel. An imaginary mass doesn't mean tachyons are purely fictional. It means they belong to a different class of objects, operating under rules that seem alien compared to our experience of the world. In simpler terms, tachyons would behave in a way that's difficult for us to visualize because they don't follow the usual rules of speed, energy, and time. They would exist in a realm of physics where light speed is just the starting point, and time isn't locked into moving in one direction. Even more bizarre is the possibility that tachyons might already exist around us, but we simply haven't detected them yet. These particles would be incredibly hard to observe because they wouldn't interact with normal matter in the same way as particles like electrons or photons. Tachyons would slip through space, crossing from one point to another, faster than light, but without the kinds of interactions that would make them visible to us. One of the places where tachyons seem to fit most naturally is in the realm of quantum physics. Quantum mechanics, with its strange and often counterintuitive rules, allows for particles that don't behave according to the everyday laws of physics. In the quantum world, particles can be in two places at once, jump between energy levels, without moving through the space in between, and even communicate across vast distances instantly through entanglement. Tachyons would fit right in with this bizarre world. Their ability to move faster than light and travel backward in time would make them a perfect candidate for explaining some of the weird behavior we see in quantum mechanics. For example, tachyons could help explain the phenomenon known as quantum tunneling, where particles seem to pass through barriers they shouldn't be able to cross, as if they've momentarily broken the rules of space and time. While tachyons remain theoretical, that hasn't stopped physicists from searching for them. Some experiments have been designed specifically to detect the presence of tachyons or to create conditions where they might appear. So far, though, no definitive evidence has been found. That doesn't mean tachyons don't exist, it just means we haven't found the right way to observe them yet. One challenge in detecting tachyons is that they might not interact with normal matter in the ways we expect. Most of our particle detectors rely on particles like electrons or photons interacting with materials in a predictable way, causing a signal that we can measure. But tachyons, traveling faster than light and possibly backward in time, might not leave the same kind of trace. They could pass through our detectors without ever slowing down or interacting with anything. Another possibility is that tachyons are only present in the early universe, or in high-energy environments, such as the core of a star or the event horizon of a black hole. In these extreme conditions, the rules of physics change, and it's possible that tachyons could exist for brief moments before decaying into more stable particles, black holes where time breaks down. Antimatter is, in many ways, the mirror image of regular matter, the kind of matter that makes up everything we see around us, from the air we breathe to the stars in the sky. But despite being the opposite of matter, antimatter behaves in ways that are intriguingly similar. For every particle that exists in the universe, there is a corresponding antiparticle, which has the same mass but the opposite charge. For instance, the antiparticle of an electron, which carries a negative charge, is called a positron, which carries a positive charge. The discovery of antimatter was a huge breakthrough in the early 20th century. Physicists like Paul Dirac, who predicted the existence of antimatter through his equations, showed that for every particle, nature seems to provide an opposite counterpart. When antimatter and matter meet, they annihilate each other in a burst of energy, producing photons, light particles. This is one of the reasons we don't see much antimatter in our everyday lives. It's constantly annihilating with matter when the two come into contact. But beyond its exotic nature and explosive interactions with matter, antimatter holds a deeper secret. One of the strangest and most fascinating aspects of antimatter is how it seems to interact with time. When we look closely at the behavior of antimatter, especially in the realm of quantum mechanics, we find that it behaves in ways that suggest a reversal of time itself. This leads us to the concept of time reversal symmetry, an idea that fundamentally challenges our understanding of how time flows. At the quantum level, particles behave in ways that are often counterintuitive and difficult to grasp. Quantum mechanics, which governs the behavior of particles like electrons, protons, and photons, allows for a range of bizarre phenomena. Particles can exist in multiple places at once, travel through barriers they shouldn't be able to pass, and even interact with themselves. But perhaps one of the strangest effects is the idea that under certain circumstances, particles, and especially antiparticles, can behave as if they are moving backward in time. This idea comes from the mathematics of quantum field theory. When physicists describe the behavior of particles, they often use equations that involve time. In most cases, time in these equations moves forward, just like we experience in our everyday lives. But when you look at the behavior of antimatter, something strange happens. The equations that describe antimatter work just as well if time is reversed. In other words, antimatter behaves in ways that are perfectly compatible with time flowing backward. Physicists sometimes describe antimatter as being like regular matter that is traveling backward through time. This doesn't mean that antimatter particles are literally moving into the past, at least not in any way we can observe. But mathematically speaking, the behavior of antimatter is identical to how regular matter would behave if it were moving in reverse. This is where the concept of time reversal symmetry comes into play. Time reversal symmetry is a principle in physics that suggests the fundamental laws governing the behavior of particles don't change if time is reversed. In many cases, if you took a video of a physical process, say two particles colliding, and played it backward, the reversed version would still follow the same laws of physics. This symmetry is particularly evident when we look at antimatter. If you imagine regular matter moving forward in time and then reverse it, you get behavior that looks strikingly similar to how antimatter behaves, moving forward in time. One famous example of time reversal symmetry involves the positron, the antiparticle of the electron. A positron behaves just like an electron, but with a positive charge instead of a negative one. In many quantum theories, the positron can be described as an electron moving backward through time. This isn't just a metaphor. When physicists solve the equations that describe the behavior of positrons, they find that the math works just as well if you assume the positron is an electron moving in reverse. This gives rise to the idea that antimatter is essentially matter going backward in time. But how does this work? In simple terms, particles like electrons and positrons exist in fields, what we call quantum fields. These fields are influenced by factors like energy and momentum, and when particles interact with these fields, their behavior is dictated by the laws of quantum mechanics. For regular particles, time moves forward through these interactions, and everything behaves as expected. But for antiparticles, there's a quirk in the math that allows them to be described as moving backward through these same fields. This time reversal behavior isn't just theoretical, it has been observed in experiments. When physicists look at the interactions between particles and antiparticles in high-energy environments, like those found in particle accelerators, they see evidence of time reversal symmetry in action. These experiments show that under certain conditions, the behavior of particles and antiparticles is indistinguishable from what we would expect if time were reversed. One particularly interesting implication of time reversal symmetry involves the Feynman diagrams, which are graphical representations of particle interactions in quantum mechanics. In these diagrams, time is typically represented as flowing from left to right. However, in some cases, Feynman diagrams show particles interacting in ways that seem to suggest time is flowing backward. For example, when a particle emits a photon and then reabsorbs it, the path of the photon in the diagram can be interpreted as moving backward in time. This interpretation works particularly well for antiparticles, which seem to follow paths that mirror the time-reversed paths of regular particles. Time reversal symmetry also has implications for the behavior of the universe at large. If the fundamental laws of physics are symmetric with respect to time, then it raises the question of why we experience time as moving forward. One possibility is that at the quantum level, time may not always behave as we expect. Particles like electrons and positrons might move in both directions in time, even though we only observe time moving forward on a macroscopic scale. But time reversal symmetry doesn't hold in every case. While the laws of quantum mechanics allow for time reversal symmetry in many processes, there are certain situations where this symmetry breaks down. One example is in the weak nuclear force, one of the four fundamental forces of nature. The weak force, which is responsible for processes like radioactive decay, behaves differently when time is reversed. This phenomenon, known as CP violation, charge parity violation, occurs when certain interactions involving particles and antiparticles don't look the same when time is reversed. This violation of time reversal symmetry is incredibly rare, but it has been observed in experiments involving particles called kaons. These particles behave slightly differently when time is reversed, suggesting that while time reversal symmetry is a fundamental aspect of many processes, it is not an absolute rule. The discovery of CP violation has profound implications for our understanding of the universe, as it suggests that time may have a preferred direction after all. Even though CP violation breaks time reversal symmetry in some cases, the fact that time reversal is possible in so many quantum processes leads physicists to continue exploring its potential implications. White holes, the opposite of black holes, and their role in time. While most of us are familiar with black holes, which are known for pulling in matter and light with such intensity that nothing can escape, white holes represent the polar opposite. Instead of pulling things in, a white hole would theoretically spit matter and energy out. In fact, nothing could enter a white hole. It only ejects. Though we've never observed a white hole, their existence is a topic of intense speculation, because they offer a fascinating perspective on the nature of time and space. The idea of white holes stems from the same equations that describe black holes. In the mid-20th century, when physicists were working with the equations of general relativity, Einstein's famous theory that describes how gravity works on a cosmic scale, they realized that the same mathematics that describe black holes could also describe a hypothetical reverse object. This would be a white hole, an entity that, unlike black holes, doesn't absorb matter but expels it. In a black hole, the gravitational pull is so strong that it warps spacetime to a degree where time and space switch roles near the event horizon, the point of no return. As you approach the event horizon of a black hole, time begins to behave more like a direction in space. Once an object crosses the event horizon, It's impossible to escape, as even light is trapped. The singularity at the core of a black hole represents a point where the laws of physics break down, and all the matter the black hole has consumed is compressed into an infinitesimally small space. A white hole, if it exists, would have an opposite kind of event horizon where nothing can enter but only exit. Imagine a boundary in space that matter and energy could emerge from, but nothing could cross into from the outside. In this case, time near a white hole would behave very differently from how it does near a black hole. Instead of time seeming to stop or compress as you approach it, time could seem to reverse or flow outward. White holes are often described as solutions to Einstein's equations in reverse. Where a black hole has an immense gravitational pull, a white hole would have the opposite effect. In a sense, if black holes represent a cosmic sink where matter and energy disappear, white holes would be a cosmic fountain, spewing matter and energy into space. Some have speculated that white holes could even be responsible for the creation of new matter in the universe, acting as a source of energy that could seed new regions of space. The notion of white holes leads us to an even more mind-bending concept: their potential role in time. In a black hole, time flows inward toward the singularity. As you approach the event horizon, time stretches out, and from the perspective of an outside observer, it seems as though time almost stops as you fall into the black hole. Once past the event horizon, all paths lead to the singularity at the center, where time as we understand it ceases to exist. The journey into a black hole is a one-way trip. There's no coming back. But what if, for white holes, time works in the opposite way? Near a white hole, time might flow outward, pushing matter and energy away from the center rather than pulling them in. In such a scenario, time might run backward in a sense, or at least appear to behave in a manner opposite to what we see around black holes. For objects near a white hole, the outward flow of matter could suggest that time itself is expelling them, pushing them further away rather than dragging them closer. To understand how white holes could exist, we need to dive deeper into the connection between black holes and white holes, particularly in the context of something called wormholes. Wormholes are theoretical bridges between different points in space-time. The idea is that a black hole on one side of the universe could be connected to a white hole on the other side. This connection might allow matter that falls into a black hole to re-emerge from a white hole elsewhere, bypassing the singularity. In this model, a black hole could act as the entry point, pulling matter and energy into it, while the white hole would act as the exit, expelling that matter back into space. In such a scenario, time would flow inward toward the black hole, but outward from the white hole. Cosmic inflation. In the first tiny fraction of a second after the Big Bang, the universe underwent a period of incredibly rapid expansion. Before inflation, the universe was a hot, dense soup of energy and particles, compressed into a space much smaller than a subatomic particle. Then, in less than a trillionth of a second, it expanded exponentially, blowing up to a much larger size almost instantly. This period of inflation is believed to have smoothed out the universe, making it remarkably homogeneous on large scales, meaning that, on average, every region of the universe looks roughly the same. Without inflation, it's hard to explain why distant parts of the universe that should never have been in contact with each other, because they're too far apart, are so similar. Inflation also laid the groundwork for the formation of galaxies, stars, and planets, by introducing tiny fluctuations in the density of matter that eventually led to the cosmic structures we see today. But cosmic inflation didn't just shape the size and structure of the universe. It also set the framework for how time behaves within it. Inflation was a period of such intense and rapid expansion that it stretched the fabric of space-time itself. During this expansion, space grew faster than the speed of light, and time itself was stretched along with it. But could the violent nature of inflation have done something even more exotic to time? Could it have split time into different directions? To explore whether inflation could push time in more than one direction, we need to look at how time is understood in physics. Time, as we experience it, seems to move in one direction, what we call the arrow of time. This forward flow of time is deeply connected to the concept of entropy. According to the second law of thermodynamics, entropy, or disorder, always increases over time. This is why we observe time moving forward, because the universe tends to evolve from a state of order to disorder. But during cosmic inflation, the universe wasn't behaving like it does today. The rapid expansion stretched space-time to such extremes that normal rules about time and space may not have applied. The universe was essentially exploding outward, and in this chaos there's a possibility that time could have been influenced in ways we don't yet fully understand. One possibility is that the violent expansion of space during inflation could have split time into different regions, where time might flow differently. In some regions, time might flow in the direction we're familiar with, forward from the past to the future. But in other regions, time could have flowed in the opposite direction, backward from the future to the past. This might seem like science fiction, but the idea comes from serious theoretical considerations. Physicists have explored the idea that time might not be as rigid as we think. In certain models of the universe, it's possible that time could behave differently depending on the conditions of space-time. Inflation, with its extreme expansion, could have created conditions where time was not uniformly directed. In fact, some theories suggest that time might have multiple arrows, depending on how the universe evolved. In a sense, inflation could have pushed time into more than one direction. One way this might work is through a concept known as time reversal symmetry, where the laws of physics are the same whether time is moving forward or backward. In the early universe, where conditions were incredibly chaotic, there might not have been a single arrow of time like we experience today. Instead, inflation could have created regions where time moved forward, and others where it moved backward. This leads to a scenario where different parts of the universe might experience time differently. In some regions, time could flow from the past to the future, while in others, time could flow backward. These regions would be separated by vast distances, and we might never be able to observe the regions where time flows in reverse. But theoretically, they could exist, hidden somewhere beyond the observable universe. One of the key factors that determines the direction of time is entropy. In our universe, entropy tends to increase over time, meaning that systems move from a state of lower disorder to higher disorder. This is why we experience time as moving forward. It's because the universe as a whole is becoming more disordered as time progresses. But during inflation, entropy might not have behaved in the same way. The universe was in a highly ordered state before inflation, and as inflation occurred, the rapid expansion could have introduced regions with different levels of entropy. In some regions, entropy might have increased, leading to the forward arrow of time we experience. But in other regions, entropy could have decreased, leading to a backward arrow of time, where events unfold in reverse. If this is true, it could mean that inflation created a kind of multiverse, where different regions have different arrows of time. In our region of the universe, time flows forward because entropy is increasing. But in another region, time could flow backward because entropy is decreasing. These regions might never interact with each other, but they could both exist as a result of the chaotic conditions during inflation. Quantum mechanics also plays a role in how we think about time during inflation. In the world of quantum physics, particles can behave in ways that seem to defy logic. They can exist in multiple states at once. They can teleport across distances, and under certain conditions, they can even move backward in time. During inflation, quantum effects would have been magnified on a cosmic scale. The tiny fluctuations in the quantum field that existed in the early universe were stretched across vast distances during inflation, creating the seeds for galaxies and cosmic structures. These quantum fluctuations also introduce the possibility that time itself might have been influenced by quantum effects. In quantum mechanics, time reversal symmetry is a well-known concept. Many of the equations that describe the behavior of particles work just as well if time is reversed. This leads some physicists to speculate that during inflation, quantum effects could have allowed time to flow in multiple directions. If inflation amplified quantum effects, it's possible that regions of the universe could have been influenced by time reversal symmetry, creating pockets where time behaves differently. One of the big questions is whether we could ever observe a region of the universe where time flows in reverse. The short answer is that it's unlikely. If inflation created regions with different arrows of time, those regions would be separated by vast distances, much farther than the observable universe. Our universe, as we see it, is incredibly vast, but it's still limited in what we can observe. Anything beyond the observable universe is effectively out of reach. So even if regions with reversed time exist, we wouldn't be able to see them. That said, the idea that inflation could have pushed time in multiple directions remains a fascinating theoretical possibility. It challenges our understanding of the universe and raises new questions about the nature of time itself. If time is not a fixed one-way flow, but something that can be influenced by the extreme conditions of inflation, then our entire concept of time might need to be reconsidered. Cosmic inflation was one of the most dramatic and influential events in the history of the universe. It set the stage for everything that followed, the formation of galaxies, stars, planets, and ultimately life itself. But it may also have created regions where time behaves in ways we can barely imagine. If inflation pushed time into multiple directions, then the universe could be much stranger than we ever thought. Time, which seems so constant in our everyday experience, could be as flexible and dynamic as the fabric of space itself. Can we stop and reverse time? We've never experienced time stopping in any direct way. Our daily lives move along a familiar timeline, with each day following the next, seemingly without interruption. However, the concept of time stopping or slowing down isn't entirely foreign to physics. In fact, time behaves differently under extreme conditions, especially in the context of the cosmos. Understanding how time might stop or restart in the future requires us to look at these unusual circumstances, where the very fabric of space-time behaves in ways we don't experience in our everyday lives. One of the most striking examples of how time might slow down or behave strangely comes from the concept of black holes. Black holes are regions in space where gravity is so intense that not even light can escape. Near a black hole, time behaves differently due to the immense gravitational pull. This phenomenon is known as time dilation. Essentially, the closer you get to a black hole, the more time slows down for you relative to someone far away from the black hole. In theory, if you were to reach the edge of a black hole, called the event horizon, time would slow down so much that it would almost appear to stop from the perspective of an outside observer. This doesn't mean that time has stopped entirely. It's still moving for you if you're near the black hole. But from an external point of view, time seems frozen. This form of time dilation shows us that under certain conditions, time can behave in ways that feel alien to our everyday experience. The extreme gravitational forces of a black hole warp space-time to such an extent that time itself appears to break down. In a sense, this is a localized example of how time could appear to stop, though only from an outside perspective. But what about the broader universe? Could time stop across the entire cosmos, not just near specific objects like black holes? To answer this, we need to look at one of the most dramatic scenarios in cosmology, the end of the universe. One potential fate for the universe is something called heat death, or the Big Freeze. This scenario arises from the fact that the universe is expanding, and as it expands, it is also cooling down. Over billions of years, galaxies drift further apart, stars burn out, and energy becomes more evenly distributed. Eventually, if the universe continues to expand indefinitely, it will reach a state where no more energy is available to do work. This is the ultimate state of maximum entropy. In a state of maximum entropy, everything would be so evenly spread out and all processes so inactive that no further change could occur. Stars would have burned out, black holes would have evaporated, and even the smallest subatomic particles might no longer interact with each other. This is where the concept of time stopping becomes more than just a theoretical curiosity. In the absence of any events, no change, no interactions, time, as we understand it, would lose its meaning. Time is, after all, a measure of change. Without change, what would time even be? In this state of heat death, time could be said to stop, because there would be nothing left to mark its passage. No clocks ticking, no stars shining, just a vast, cold, empty universe where everything has reached a final state of stillness. This scenario is not something that would happen tomorrow or even in a billion years, but it's a possible end for the universe billions upon billions of years from now. In this theoretical future, time might cease to exist in any meaningful way, frozen in a state of perfect equilibrium. The idea of time stopping is, in itself, a mind-bending concept. But what's even more intriguing is the question: could time restart? Is there a scenario where, after time has stopped, the universe could somehow reawaken and time could begin to flow again? This brings us to the Big Bounce theory. The Big Bounce is a cosmological model that suggests the universe might not end in a heat death or a final collapse, but instead could go through a cycle of expansions and contractions. In this model, the universe expands, as it is doing now. But at some point in the future, that expansion could slow down and reverse. Instead of drifting further apart, galaxies and other cosmic structures would start to collapse back together. The universe would shrink, condensing all matter and energy into a smaller and smaller space, potentially returning to a state similar to the conditions at the beginning of the Big Bang. In the Big Bounce model, the universe reaches a point of maximum contraction, what some call a big crunch. But instead of collapsing into nothingness, the universe could bounce back, starting a new cycle of expansion. With each new cycle, time would essentially reset. The end of one universe, marked by a contraction, would be followed by the birth of a new one, marked by an expansion. In this scenario, time would stop at the moment of maximum contraction and then restart when the new expansion begins. What's fascinating about the Big Bounce theory is that it suggests time might not be a one-way street with a definite end. Instead, time could be cyclical, with periods of activity followed by periods of dormancy. Each bounce could represent the restart of time, with the universe evolving in new ways each time it begins to expand again. One of the most intriguing aspects of the Big Bounce theory is that it not only suggests a cyclic nature to the universe, but also hints at the possibility that each new bounce might come with entirely different laws of physics, or at least new configurations of energy and matter. This means that the restart of time wouldn't simply be a return to what we know now. It could lead to a universe with entirely new properties, where time might flow differently, or where events unfold in ways that are radically unfamiliar to us. Each cycle of the universe could be its own distinct version of reality, with time as one of the elements that gets reshaped each time the universe collapses and expands again. In such a model, time could be viewed as having a kind of stop at the moment of the universe's maximum contraction, but this stop wouldn't be a permanent end. Rather, it would be a pause between one cosmic cycle and the next, much like how a pendulum reaches its peak height and briefly halts before swinging back in the opposite direction. This temporary cessation of time is tied to the state of extreme density and gravity during the collapse phase of the universe. Under such conditions, similar to the effects we see near black holes, time could slow down to the point where it essentially freezes, only to restart when the bounce occurs and the universe begins its next expansion. This idea of time pausing during the Big Crunch aligns with what we know about how gravity affects time. As the universe contracts, gravity would increase dramatically, warping space-time to such a degree that time as we experience it could be brought to a near standstill. This would be similar to the extreme time dilation effect seen near the event horizon of a black hole, but on a universal scale. Every point in the universe would experience this near halt in time, as space itself would be collapsing inward. From the perspective of any potential observers, if such beings could exist in such extreme conditions, time would slow to an imperceptible crawl as the universe reached its critical point of contraction. However, in the Big Bounce scenario, this pause in time wouldn't mark the end of everything. Instead, the universe would undergo a rebound, a moment when the intense pressure and density of the contracted universe cause it to explode outward once more, much like the Big Bang that initiated our current cycle of time and space. With this expansion, time would begin to flow again, and the universe would be reborn with new conditions for life, matter, and cosmic evolution. Some versions of the Big Bounce theory suggest that the information encoded in the structure of the universe, such as the distribution of galaxies, stars, and cosmic forces, might leave an imprint that persists across cycles. If this is the case, then the restart of time in each cycle might not be a complete blank slate. Instead, remnants of the past could influence the new universe, much like how genetic information from previous generations shapes the evolution of life. This opens up the possibility that the restart of time could be influenced by what came before, even if the previous universe collapsed into a near singularity before bouncing back. The patterns of cosmic evolution, the laws of physics, and even the structure of time itself could evolve with each new cycle, shaped by the experiences of the past while moving forward into new configurations. In this sense, the restart of time isn't just a repeat. It's a continuation of a cosmic story, one that keeps building on what came before, even as each new universe brings fresh beginnings. One of the biggest challenges in understanding whether time can stop and restart in the future is that we don't yet have a complete theory that unites general relativity, which governs the large-scale structure of the universe, with quantum mechanics, which rules the smallest scales. The intersection of these two domains is where many of the mysteries of time, including the potential for it to stop and restart, lie. At the heart of these mysteries is the nature of space-time itself, which behaves very differently under extreme conditions, like those found at the moment of the Big Crunch or Big Bounce. Could we manipulate time by altering space? The relationship between space and time is fundamental in general relativity, and the warping of space-time is a real phenomenon that happens around massive objects. Black holes, for example, create such intense gravitational fields that they warp space-time dramatically. Near the event horizon of a black hole, time slows down to such an extent that for an external observer, it appears as though time almost stops entirely for anything near the black hole. This shows that by altering space through gravity, we can change the flow of time. But black holes are not something we can control or manipulate at will. To realistically manipulate time by altering space, we would need to create conditions that allow for the controlled bending of space-time. In theory, this could be done with extreme gravitational fields, but we currently have no means of generating or manipulating gravity on such a large scale. However, by understanding how gravity affects time, we gain a glimpse into the possibility that controlling space could, under the right conditions, influence time. One speculative method of bending space-time involves the idea of creating artificial gravity wells. If we could somehow manipulate matter to create a localized region with immense gravity, we might be able to slow down time within that region. The science behind this idea is that time runs slower in stronger gravitational fields. So by controlling gravity, we could potentially control time. But the problem with this idea is that the energy and mass required to create such a gravity well would be astronomical, far beyond our current technological capabilities. The Alcubierre drive is another theoretical concept that allows for faster-than-light travel by contracting space in front of a spacecraft and expanding it behind. This drive doesn't violate the laws of relativity, because it doesn't move the spacecraft faster than light through space. Instead, it moves space itself, effectively allowing the spacecraft to travel faster than light relative to the space around it. The Alcubierre drive offers a potential way to manipulate time, because faster-than-light travel is closely linked to time dilation and other relativistic effects. If you could travel faster than light by altering space, you could, in theory, also manipulate your position in time. The ship moving through space with an Alcubierre drive could reach a distant point in space far more quickly than light could travel there, effectively arriving in the future. However, the same drive could, in principle, be used to move backward in time if space is manipulated in the opposite direction. This creates the possibility of time travel by altering the structure of space-time itself. But, like with wormholes, the energy requirements for an Alcubierre drive are currently beyond anything we can generate. It would require negative energy or exotic matter, which we have not yet discovered or learned how to produce. The biggest question: could the universe itself reverse time? Let's start by considering the broader context. The universe we live in is currently expanding. Ever since the Big Bang, a cataclysmic event that occurred around 13.8 billion years ago, the universe has been steadily growing. Galaxies are moving away from one another as space itself stretches out. This process, known as cosmic expansion, has been observed and measured, leading scientists to believe that the universe is getting larger over time. But if the universe can expand, could it also collapse? Could the expansion slow down, stop, and then reverse, leading to a scenario where time itself starts moving backward? To explore this question, we need to dive into some key scientific theories about the universe's fate. One of the most important concepts in this discussion is the Big Crunch. The Big Crunch is a theoretical scenario in which the expansion of the universe eventually halts and reverses, causing everything in the universe to collapse back into a single point, much like the Big Bang, but in reverse. The idea behind the Big Crunch is simple. Right now, the universe is expanding, but that expansion could slow down and eventually stop. If the force of gravity becomes stronger than the force driving the expansion, which scientists call dark energy, the universe could start contracting. Galaxies would begin moving closer together, stars and planets would collide, and eventually, everything would merge into a single, incredibly dense point. In this scenario, the universe would essentially unfold in reverse, leading to a cosmic collapse. What's fascinating about the Big Crunch is that it raises the possibility that time itself could reverse. In our current expanding universe, time seems to flow in one direction, forward. This forward motion is linked to entropy, the idea that the universe is moving toward a state of greater disorder. But if the universe begins to contract, could entropy reverse as well? Could time flow backward, causing events to happen in reverse order, just as the galaxies collapse inward? To understand how time could reverse, we need to talk about entropy and the arrow of time. Entropy is a concept from thermodynamics that describes the level of disorder in a system. In general, systems tend to move from a state of order to a state of disorder. This is why, for example, ice melts into water and why stars burn through their fuel and eventually die. The universe as a whole is also moving toward a state of higher entropy, more disorder. The arrow of time refers to the fact that time seems to move in one direction, from the past to the future. We remember the past, we live in the present, and we anticipate the future. But the arrow of time is deeply connected to entropy. As the universe expands and entropy increases, time moves forward. But what if entropy could decrease? What if, in a contracting universe, order increased rather than decreased? This is where the idea of time reversal comes into play. In a universe where entropy decreases, where things become more ordered over time rather than more disordered, it's possible that time could reverse as well. If the universe were to collapse into a big crunch, entropy could decrease and time could flow backward. Events would unfold in reverse, with galaxies collapsing, stars unburning, and life moving backward through time. It's a wild concept, but it's one that some scientists believe could be possible under the right conditions. One of the key factors that will determine whether the universe could reverse time is dark energy. Dark energy is a mysterious force that is driving the current expansion of the universe. We don't know much about dark energy, but we do know that it makes up about 70% of the universe's total energy content, and it's responsible for pushing galaxies apart at an accelerating rate. If dark energy continues to dominate, the universe will keep expanding forever. This scenario is known as the Big Freeze or heat death of the universe. In this case, the universe would continue expanding until galaxies are so far apart that they can no longer interact with one another. Stars would burn out, black holes would evaporate, and the universe would become a cold, dark, and empty place. In this scenario, time would continue to move forward, and entropy would continue to increase until the universe reaches a state of maximum disorder. But what if dark energy changes over time? Some theories suggest that dark energy might not be a constant force. If dark energy weakens or changes direction, it could allow gravity to take over and cause the universe to collapse. This is where the possibility of a big crunch and the reversal of time comes into play. There's another theory that builds on the idea of a collapsing universe, but with a twist. This theory is known as the Big Bounce. In the Big Bounce model, the universe doesn't just collapse into a singular point and end. It bounces back. After collapsing in a big crunch, the universe could rebound in another Big Bang, starting a new cycle of expansion. In this model, the universe goes through endless cycles of expansion and contraction, with each cycle potentially creating new galaxies, stars, and even new forms of life. In some versions of the Big Bounce, time could reverse during the contraction phase, only to start moving forward again after the next Big Bang. This would mean that time, like the universe itself, is cyclical. The past and the future could be intertwined, with each cycle of the universe playing out in different ways. What makes the Big Bounce theory intriguing is that it offers a way to avoid the finality of a big crunch or a big freeze. Instead of the universe ending in a collapse or freezing into a lifeless void, the universe could continually renew itself, with time moving forward in some cycles and backward in others. While this is still a speculative idea, it's one that challenges our linear view of time and opens up the possibility of a universe where time itself is reborn. Another angle to consider when thinking about time reversal on a universal scale is the role of quantum mechanics. In the world of quantum physics, time behaves very differently than it does in our everyday experience. On the quantum level, particles can exist in multiple states at once, and some processes appear to be reversible. In fact, the fundamental equations of quantum mechanics don't necessarily require time to move in one direction. This leads to the idea that, on a quantum level, time might be able to flow backward just as easily as it flows forward. Some physicists speculate that if we could better understand the relationship between quantum mechanics and gravity, through a theory of quantum gravity or something like string theory, we might be able to unlock new insights into the nature of time. Perhaps time reversal, at least on a microscopic scale, is already happening in ways we don't yet fully understand. One final possibility to consider is the idea of the multiverse. The multiverse theory suggests that our universe is just one of many parallel universes, each with its own laws of physics, its own history, and perhaps even its own version of time. In some versions of the multiverse theory, other universes could have different arrows of time. While time in our universe seems to move forward, other universes might experience time flowing backward. If the multiverse theory is correct, then time reversal could be a common occurrence in some universes. In fact, there could be entire universes where time behaves in ways that are completely alien to us, where cause and effect are reversed, and the future leads to the past. While this idea is highly speculative, it raises fascinating questions about the nature of time and whether it's something that can be altered or experienced differently in other parts of the cosmos. The grandfather paradox and the dangers of time travel. The grandfather paradox is one of the most well-known and thought-provoking puzzles in the realm of time travel. It raises a simple yet profound question. What happens if you go back in time and change something so fundamental that it affects your very existence? The classic example goes like this. Imagine you travel back in time and stop your grandfather from meeting your grandmother. If they never meet, your parent is never born, and in turn, you would never be born. But if you were never born, how could you have traveled back in time in the first place to prevent their meeting? This creates a logical loop, a paradox, where your actions in the past erase the very future that allowed you to exist in the first place. The paradox forces us to question the nature of cause and effect. We typically think of time as a one-way street where causes lead to effects in a linear fashion. You are born, you live your life, and the things you do affect what happens next. But time travel, especially to the past, turns this on its head. Suddenly, the future can affect the past, and the distinction between cause and effect becomes blurry. This is where the grandfather paradox really gets interesting. Could changing the past destroy the future? Let's explore this further. If you go back in time and change something significant, like stopping your grandparents from meeting, you're effectively rewriting history. But the moment you rewrite history, the future as you know it ceases to exist. The new timeline you've created no longer includes you because you've erased the very conditions that led to your existence. In this way, the grandfather paradox creates a kind of logical dead end. The past and future can't coexist in the same timeline if the act of going back in time undoes the future. But could there be a way around this paradox? Some theories suggest that instead of creating a logical loop, time travel might create alternate timelines or parallel universes. In this scenario, when you go back in time and change something, you don't erase your own existence. Instead, you create a new timeline where events unfold differently. In this new timeline, your grandparents never meet, and you are never born. But this doesn't affect the original timeline, where you came from. You continue to exist in the original timeline, but the new timeline now plays out with different rules, essentially branching off into a parallel universe. This idea of parallel universes offers one possible solution to the grandfather paradox. If every time you travel to the past and make a change, you create a new, separate timeline, then the paradox is avoided because you're not erasing your own existence. You're just creating a world where things happen differently. This is a concept that's often explored in science fiction, where time travelers hop between multiple realities, each with its own version of history. Another possible way to resolve the grandfather paradox comes from the idea of self-consistency in time travel. This theory suggests that any actions you take in the past were always part of history to begin with. In other words, if you go back in time, whatever you do has already been factored into the timeline. So, even if you try to stop your grandparents from meeting, you'll find that you can't. Something will always intervene to make sure that they meet and that you are eventually born. The timeline protects itself from changes by ensuring that everything unfolds in a way that maintains consistency. This idea of self-consistency eliminates the paradox by suggesting that time travel doesn't allow you to truly change the past. You can go back and interact with past events, but those events will always play out in a way that ensures the future remains unchanged. For instance, even if you attempt to prevent your grandparents from meeting, something else will happen that ultimately brings them together. Maybe they meet in a different way, or someone else takes your place in bringing them together. In this view, time is more like a closed loop where everything that happens is self-contained and self-consistent. Another fascinating possibility involves the concept of quantum mechanics. In the quantum world, particles can exist in multiple states at once, and outcomes aren't always definite until they are observed. This opens the door to the idea that time itself could behave in ways that are far less rigid than we imagine. Some physicists speculate that the grandfather paradox might be resolved through quantum mechanics by allowing multiple outcomes to exist simultaneously. When you go back in time, you might both stop your grandparents from meeting and fail to stop them, with both possibilities coexisting in different quantum states. In this quantum view of time travel, the paradox might be avoided because the act of changing the past doesn't necessarily erase the future. It simply splits the universe into different quantum states, each representing a different outcome. In one state, you exist because your grandparents met. In another, you don't exist because they never met. Both outcomes exist simultaneously in different quantum branches, and the paradox is avoided. But beyond these theoretical solutions, the grandfather paradox also forces us to confront deeper questions about the nature of time and reality. If time travel were possible, what kind of world would we live in? Would the past be fixed, or could it be rewritten? And if it could be rewritten, what happens to the future? The paradox challenges our understanding of causality, the idea that causes lead to effects in a straightforward way. It suggests that time, far from being a simple line, might be something far more complex and multidimensional.